This is one of the many places I've been to around the globe looking at volcanoes, and I've actually spent 3 years, been to the Cascades on 3 separate occasions. But I was always particularly fascinated by the Cascade Range because of the eruption of Mount St Helens in May 1980, which sort of drew the world's attention to that particular volcano and the disaster that befell the people who were affected by it. But also the fact that it was a turning point in a lot of ways of knowledge in terms of volcanic eruptions and predicting them, and it was a rapid learning experience that people gained from that, which has been applied and improved upon in the years that have followed. So Cascades Volcanoes, as I say, I've been there, been to see them on 3 separate occasions, and done a fair bit of background reading about them. This is the presentation I put together to give you a more detailed knowledge of the volcanoes. Just a few key facts about them first of all. It's about 600 miles between the one that's the volcano that's regarded as the furthest north, and depending which source of information you use, it's difficult. What some sources quote Mount Garibaldi in Canada, northwest Canada in British Columbia, whereas others mention Mount Meager. But about 600 miles between the furthest north and the furthest south of the Cascades. And these are referred to really as the modern Cascades, because there was an earlier formation of the Cascade volcanoes, which were active many years before that and had largely been eroded down and have been built on by later volcanoes. So there are 13 major volcanic centres, and lots and lots of others. And if you take any one particular volcano, like for example, I could mention Newbury, there's about 400 different spots where lava has appeared at the surface in some form or other of the Newbury volcano. So they are there's huge numbers of sites there, but very broadly 600 miles north to south, but a lot narrower east to west, probably about 50 miles or so. As you can see, they stretch from California. This particular slide stops at the Canadian border, Washington, but they do stretch into British Columbia as well. Just the current plate tectonic situation. The Juan de Fuca plate is a little plate. It's the remains of a much larger plate, but it's gradually been subducted beneath the North American plate. It's a convergent plate margin between a slab of oceanic crust, oceanic lithosphere, and a thick continental plate, the North American plate. And the oceanic plate, as I'm sure that you all know from plate tectonics, is denser, it's thinner, and so that's the one that slides down and disappears into a subduction zone beneath the North American plate. Friction within that causes partial melting of the more silica-rich element, and then that, being lighter, then rises up through the crust and pops out at the surface to form the volcanoes. One key point, there isn't an ocean trench. If you look at the situation alongside South America in a similar position, where you've got the Pacific plate sliding underneath the South American plate. There's a very clear, deep ocean trench, as there is around much of the Pacific. But there isn't on here, and the reason is thought to be the fact that there's so much sediment that's coming down off the land, it's actually filling the supposed trench that would be forming as the plate goes down, and so there's a very thick layer of sediment. So this is the Juan de Fuca plate, and these are the Cascades Volcanoes, as I say. These are all divergent margins, not very far away from the coastline, as you can see. Pacific, this is a convergent margin here, here, here. This is called a Gorda plate, or a mini plate. Oh, sorry, that Gorda plate is further south. It's the Explorer plate in the north. And that is the situation in the Canadian, North American border, roughly, where the Juan de Fuca plate is going down, as you can see. But not a deep trench there.
Are those ridges still spreading?
Sorry?
Are the ridges still
Yes,
spreading?
yes, they are, yeah. Yeah, I mean, of course, like most mid-ocean ridges, they're 4 kilometres below sea level, and you know, there's new crust forming, new lithosphere forming at those spreading ridges. But all of it is below the surface. At no point does it get above the surface, so it's, you'll be getting pillar lavas, for example, forming on the seabed down there. Just to take you back through time, so 150 million years ago, the western edge of North America was situated near a subduction zone where an older plate called the Farallon plate was being subducted beneath the North American plate, and there was volcanic activity taking place even 150 million years ago. And then you get this early volcanic arc. I mean, the typical situation you might expect is that subducted material, as the plate goes down and you get friction below the surface, deep down in the upper mantle, you get material rising up and producing volcanic islands. You often get volcanic islands. And these were the beginnings of the old Cascade Range. A volcanic island arc, a set of volcanic islands forming over the subduction zone. But that was out at sea. Similar situation to modern day Indonesia or the Philippines. And then you'll see a lot of reference, if you look at any references on this, to the fact that there's been continental accretion developing. So materials that were formed, out at sea, volcanic island arcs, for example, they were subsequently carried by the plates towards the edge of the North American continent and effectively welded onto the edge of the continent, and the continent expanded as a result. So if you look at a geological map of North America, the oldest part is the vast majority of it in the centre is the Canadian Shield. But then on to the west of it, you've got progressively younger pieces of crust that are formed over time. One of the major ones that gets a reference is the Silesia terrain. It accreted during that time. Large basaltic lava flows form part of the coast range and part of the Cascades range. Collision of the Silesia terrain and other small oceanic terrains helped to initiate the development of volcanic arcs along the edges. And there's a slide which sort of illustrates that. So you've got oceanic plates approaching North America from the west, containing rock and sediment of a seamount. The package of rock may be several different terrains faulted together. And once they came into contact with the continental lithosphere, that was just piled up on the edge there. And this is the material here. These terrains are what the Cascade Range have been built upon. Multiple foregrounded accreted terrains, mostly hidden beneath younger Cainozoic rock, they form the basement rock of, it mentions Oregon because this particular slide is taken from the geology of Oregon, roadside geology of Oregon, the book I got this from. $55 to 17 million years ago, this is when you got the real development of the older Cascades. When it was the Cascade, the original earlier Cascade volcanoes, of which these form now the basement of what the modern Cascades have been built upon. But they were forming around that time, and then for some reason there were subtle changes in. They believe there were subtle changes in the plate tectonic situation for a while after the older Cascades, when they ceased to become active, and there was possibly tension. As the plates were moving apart, they were no longer colliding, but were being pulled apart. And just for a while, I say, we're talking, 10 and 15 million years. You weren't getting the subduction anymore, and what you were getting instead was tension, which allowed passageways to bring material up from the mantle. And then spread out the Columbia River basalts. This gigantic area of a basalt plateau that covers, not completely covers 3 states. It's found in Idaho, it's found in Oregon, and it's found in Washington. But it's hundreds of miles across and very, very thick, as you'll see from the slides I'm about to show you in a little while. So you had the Columbia plateau basalts created, named after the Columbia River, which is cut down into them. And then this is when the new subduction zone developed, and you started to get continued subduction of the Fuca plate, and this is when the modern volcanoes started, the modern Cascades started to form. And over the years, it's created quite well-known volcanoes. There are an awful lot of them, as I say. I try to remember the names of them all, but some of the most well-known are Mount Rainier, Mount St. Helens, and Mount Hood. Particularly over the last 10 million years, they've been very active. So, what I'm going to do now is to if you like, take you on a journey, starting in the north, where not the most northerly of the volcanoes, but the ones that I've been to visit. And this is Mount Rainier, which is not far away from Seattle, and in Washington State. And what we'll do is do a journey south. So we'll start with Mount Rainier, we'll look at Mountain Helens, we'll look at Mount Hood, the Columbia River basalts, the Newberry volcano, and I'll leave the last one as a bit of a surprise. So this is Mount Rainier, the highest mountain in the contiguous mainland USA. There is a higher mountain in Alaska. That's why I didn't say the highest mountain in mainland USA, but contiguous USA, Mount Rainier, over 14,000 feet. It's actually very close to some of the not volcanoes, mountains in Colombia. I think Pikes Peak is over 14,000 feet, so there's not a lot in it, but this is the very highest in mainland USA. So about 700,000 years old. They believe it was over 16,000 feet, but like many of these volcanoes, the upper part has just been either blasted away or the central sections collapsed away through the formation of a caldera. And it's not all that active. There have been 4 eruptions in 4,000 years. So it's not erupting all the time, not even every 100 years but 4 eruptions in 4,000 years. Mostly andesite, although quite a number of the Cascade volcanoes, it depends to a certain extent how long magma sits in the magma chamber as to whether the heavier materials settle out and allow more silica-rich magmas to be erupted. So just occasionally you get rhyolite and dacite, the very silica-rich ones. So the basement rocks in the area, these are the ones it sort of sits on. You've got 40 million year old Ohanipikosh formation. Those were then folded and eroded, and the later activity produced Stevens Ridge and Volcanic Peak formations. These are all before Mount Rainier formed. And then there was an intrusion of a huge granite pluton, which is, and the surface has been worn down to expose that granite pluton, because that will have formed at considerable depth. And then eventually you had these the new material cut through all that, and it come to the surface and build up Mount Rainier. And the big issue with Mount Rainier is the danger it poses from lahars, basically massive floods. It's a potential of a real disaster, and just to alert you to the fact, there was a mud flow. It released a cubic mile of debris. When the volcano, if it were to start erupting, this has got 26 glaciers on its flanks. The first thing that will happen will be an awful lot of meltwater will be created. That will mix with a lot of the softer ash on the sides, wash down into the valleys below. But when we talk about half a cubic mile, it's difficult to comprehend. But that one, it covered 100 square miles before entering Puget Sound. And if that happened today, it would sweep across an area that's heavily populated and kill thousands and thousands of people, unless they were evacuated to somewhere with a warning. So this is what Mount Rainier looks like. This is from the eastern side. and I believe that that's the Emmons Glacier. One of the things I ought to mention, if you do happen to want to choose to go to see the volcanoes, really you've got a limited time opportunity in terms of the year. I think if you go any time before about April until really the season would start at about April and continue to round about October. But if you went in the winter, all the mountain roads would be inaccessible. And the best time to go is really, it's really July. I think it's the perfect month to go. That's when the snow starts to melt away, and you can actually take the mountain footpaths. So this is another picture, another view of it from the southeastern side. Again, this is the summer flowers out. This was taken in July 2009. So 2009. I think we've moved around to the southern side now, and as well as having one of the largest glaciers in terms of width, it's also got the longest glacier in North America, the Carbon Glacier. I'm not sure that picture actually shows the Carbon Glacier. I've got another picture further down. And that's actually the exposure of the granite that's been polished by the ice. You know, as ice has moved across it, it's left striations. I think that's what the plate explains there. That's the Tatoosh granite. This is the view of it from so-called Reflection Lake. This we stayed for a couple of days at a lodge on the southern side, Paradise it's called, and so we were able to explore that for a couple of days. This is the glacier. I mean, this is one of the, obviously the meltwater coming out the snout of the glacier here. It's covered in debris, so you might not recognise it as a glacier as such. But that is the ice that's coming down from here. Mount St Helens. I think everybody, a lot of people have heard of Mount St Helens, certainly of people of my generation, and it's used as an example in schools and colleges to teach you about the effects of a major eruption. It's actually one of the smallest of the Cascade volcanoes. It's the youngest. Only 37,000 years old, although there is an older volcano that it's built upon. And most of the growth took place in the last 2,000 years. Up to May 2018, it was 9,677 feet high, but its height now is 8,364. The older deposits were basalts of the new volcano when it first started to form, the new volcano, basalt and andesite. But certainly the most recent eruption that has taken place in 1980 produced very pale andesite, and then after the eruption and blowing off of the upper part of the volcano, there's the most recent manifestation is a lava dome of dacite. So this was just the timetable of events. Nothing had happened until March the 20th of the year, so it's really only we're talking a couple of months, 8 weeks, 8-9 weeks. Few earthquakes, and they located the epicenter, the foci of the earthquakes is coming from beneath the main crater of Mount St. Helens. And then there were more and more of them, which they came to believe were actually magma working its way up towards the surface. Rather than build up the whole volcano, it tended to produce a bulge on the northern side. The bulge had grown to 300 feet high. Very big earthquakes in early April, and then to mid-April, and by the end of April, 400 feet high. I mean, you think of a bulge, so we say, what's it called, the BT tower? That's 600 feet high. I mean, it's something 2/3 of this is a bulge on the side of a mountain that's that big. And cracks were appearing in it, and they realised that it was going to erupt. They'd got very little doubt about it, so they ordered the evacuation of the local area. But of course, there were people camping out in the forests to the north of the volcano, a long way away. There were scientists located quite close in, monitoring it and measuring the size of the bulges and collecting samples and gases coming off it. But then they had this catastrophic eruption, 8:30 in the morning, and huge landslide down one side. I think it's difficult to know precisely the mechanism that happened there. Was it because they all happened almost simultaneously. The side of the volcano gave way, a great section slab slid down, and at the same time out rushed a major blast from the side of the volcano with all the gas and the ash and the lumps of rock and everything else that was blasted out. Now, whether it was the blast that triggered the landslide, or whether it was a landslide that released the space to trigger the blast, it's difficult to decide. But the two happened more or less together, and you had a lahar created, a debris flow of rock, mud, ice and water west for 25 kilometres. If you want to go onto the internet and see lots of images, films of the event, you can find it. There's so many films there. I might have put one in on this presentation, were it not for the fact that they all seem to be advertising something, rather than leave that up. But 57 people killed, only 57, but I mean, some of those were like 15-20 miles away from the actual volcano's summit, the main crater. It created an ash column 20 kilometres high, and ash was spread across the states and high into the atmosphere. I mean, I don't know how many people remember May 1980, but we'd actually in Britain had quite a glorious spring, the weather. And then after that, the summer was horrible. You probably, a lot of you wouldn't have been around at the time, so, or quite young, but it was And then, as I say, the last thing to happen was a small lava dome created at day site. And as I mentioned earlier, I mean, one of the main positives that come out of it was the fact that it's aided the planning of volcanic eruptions and predictions of eruptions since then. That is the aerial view. This is Spirit Lake. There is a visitor centre up near Coldwater Lake. There's also the Johnson Ridge Visitor Centre, which is around here somewhere. Unfortunately, the Johnson Visitor Centre, named after David Johnson, who was actually monitoring the volcano at the time and got killed, lost by basically he spent 10 weeks studying it, and he was as close as people dared to get, but he of course was killed, and they built a very big new massive visitor centre there. But unfortunately Lahar in the last couple of years has actually cut it off, and there's no easy road to it anymore. So they had to evacuate the place. And they're hoping to rebuild the road. They did rebuild it once, and then that failed again. The bridge to it across the river failed. And so they decided they needed a more substantial repair. And this is Spirit Lake from the eastern side. You can see that this is just one example of one of the trees that was blasted away, but all of those are individual logs of massive trees like this that ended up in the lake. There were tens of thousands of trees that ended up in Spirit Lake. Further away from the eruption site, the trees weren't necessarily broken away, but they were just stripped of their branches and vegetation, and they just sort of stand almost as monuments to it now. And this is the view of the caldera that's been created, and this is the new lava dome in the centre, from various views. We took the group this year to I took a group to Mount St Helens this year, and this is the view we would have got if the weather had been kind to us.
The only day, wasn't it, when the weather?
Yeah, I mean, most of the time we were in the area, the weather was glorious. But the one day, and it does take, it's like several hours of coach journey up to it, and it was nothing but fog. You couldn't see a thing there, which was very unfortunate. But these were some pictures I took in 2010. I was fortunate to invest in a helicopter ride over the volcano, and we got a real close-up view. The helicopter took you inside the caldera. This is the only place in the world, I think, where glaciers are actually growing. Everywhere else in the world, glaciers are retreating because of global warming, supposedly. Maybe not everywhere, but just about everywhere. But in Mount St Helens, a glacier has formed, and it's actually growing as each year goes by. And trying to work out where the snout of it is difficult because it's covered in ash. I think this side of it is coming down here. That's the view looking to the north. towards Spirit Lake, and that's Mount Baker in the distance. And this was taken this year. This is from the south side. The following day, we did the north side one day, and on the south side the following day. And they had the lahar come down. This is the deposits of the lahar with new vegetation growing. I mean, it's had 40 years to grow, more than 40, 44 years to grow. So there's a fair amount of vegetation there. Well, that's the remains of one of the trees that were just washed away by the lahar. And that's it from the south side. So I've already talked about the Columbia Plateau basalts. I'm going to speed up a little bit because of the late start. I think we only need to speed up to get through some of these later slides. But the Columbia Plateau basalts, as I mentioned, changes in plate movement caused the crustal tension. And the most vigorous eruptions took place 17 to 14 million years ago. 99% of the lavas were erupted then. But they didn't actually end, the final one, until 6 million years ago. And they're named after the Columbia River, gigantic river which drains west from the central part of North America, and formed a major routeway to the west by the early settlers, early American settlers, not the native nor the original settlers, of course, but when Oregon and Washington were settled by trying to be politically correct now, by the Southern and the white settlers that had emigrated to the USA and were wanting to open up the West. They said that they reached a point where they had to, some of them, the ones who were tempted by gold, they headed south and went to California, and the ones that wanted to become farmers, they headed into Oregon. So that's, this is the river, and this is all the plateau basalts, or all at the surface anyway, and go down deeper than that. Major routeway. And you can see that the plateau basalts there, there's an awful lot of columnar jointed in it. So moving on, so we're into Oregon now. We've moved through the plateau basalts. So we've been to Portland in Oregon is the major city in the area, and we've moved south to Mount Hood, which is easily visible from Portland. It's 60 miles away. And this is the fourth highest peak in the Cascades. It's accessible all year round, and it's a massive centre for skiing and snowboarding. It's the advantage being, of course, that the snow on it all year round, and it's got chairlifts up the side to take skiers and snowboarders to the higher levels. Again, it's quite an old volcano, more than 500,000 years old, but very active, 15,000 to 30,000 years ago. And then it was in a major eruptive period 1,500 years ago, but it has erupted in recent times. You can see 1700s and 1800s, odd smaller eruptions. And one of the things it's famous for is the fact that this view from the north is actually the view, if you go to the cinema and you watch a Paramount picture, that's the volcano that's in the picture, and they all show Paramount pictures. And this is the view from the south. It's the same. It's not so impressive looking from the south. You can see the chairlifts going up the side, and these are the snowboarders walking along. Now, one of the ones that doesn't often get a mention, Newbury. It's the largest volcano, depends on how you define size, but possibly the largest volcano in the Cascades. 400 different vents. It covers 1,200 square miles. Formed over half a million years ago. All sorts of different eruptions over the years, everything from basaltic material right through to the highly silicic obsidian and pumice. And the best description they come up with is it's a shield-like composite volcano. It's got a very gentle slope angle to the edge, and you'd hardly know you'd actually climbed or driven up a volcano, and you were in the central area of it. The slope angle is so, and it's because there have been all sorts of eruptions over the years, and as the magma chambers empty, what's happened is the central sections collapsed in, so it's never really built up to any massive height, and there have been several different calderas created, the youngest ones being in the very centre now, the older ones the furthest out. And there's a little map next, which shows you, this is 30 miles, so from there to there is about 30 miles, but that's another 60 miles. These are lavas that have flowed from this area up to 60 miles away from its main centre. And the place to go if you want to get spend time looking at it, and other volcanoes of the Cascades, is Bend, a place in Oregon. We spent on 2 nights at Bend. This is Lava Butte, or Lava Butte. I think it's pronounced Butte, Lava Butte, which is a cinder cone, which you can walk around the rim of quite comfortably in about half an hour to do the circuit and climb up the edge and walk around, and you get a spectacular view from the top. If you look down into the distance, quite some distance, you can see basalt lava that's flowed around the area close by, fairly recently, because there's little or nothing in terms of vegetation on it. This is from the rim of the cinder cone, major rootway to the south. Now, one of the features, probably perhaps the most interesting feature of the Newbury volcano is the fact it's got something called the big obsidian flow. And this is a massive, obsidian is a very viscous, very sticky, it's a very slow moving material, so it won't flow very far, but it's crept out of a fissure and spread out a short distance, but that's quite high. We're talking around about 100 feet, maybe more than that in thickness, but it's pure obsidian. If you walk around and through it, this is what it's like. And there's a piece I've taken a picture just to show if you wanted to take the risk of collecting a sample. You're not supposed to take any samples, and so I was very wary of that. If you got to the airport and they found you taking rocks out of the area, you could be in trouble, and I wouldn't want to risk that myself. But there's some lovely pieces of obsidian. Lastly, this is the one that I didn't mention. I think this was the most spectacular site that we saw in the whole trip. Crater Lake. A volcano called Mount Mazama basically blew the top off 7,700 years ago. It formed a layer of deposit which stretched right the way across Oregon State and further. The layer of ash that was created right up near the coast. It has been found in ice cores from Greenland. 12 cubic miles of material released, and that's round about 10 times the amount of material that blew out of Mount St. Helens in the 1980 eruption. Just to put it into perspective. Millions of tons of sulfuric acid released into the atmosphere, dropped the world's temperature by about 1 degree Fahrenheit almost instantly. And the magma chamber emptied, and then the whole central section collapsed to form a deep hollow, which then took 200 years to fill. Any rainfall, any snowmelt that fell into it would fall on the sides and at the bottom. And when it melted, it built up the lake. But it took 200 years to fill the lake before any water could escape out of the lake. And the lake is now almost 2,000 feet deep. It's the deepest lake in North America. Continued activity, so that's 200 years, but it continued for another that was 7,700 years ago, but the final piece of activity was 5,000 years ago. So there were eruptions over that period, 7,700 to 5,000 years ago, and these built up what's one of the islands that peaks above the lake level, called Wizard Island, and also if you were at sea, you'd call it a seamount, but I don't know what the word is but it's a submarine mountain, a large dome called Meriam Cone. And these are the last 2 or 3 pictures I've got. I mean, it really is that colour, it's so striking, you get to it and it's such a vivid blue. That's Wizard Island. And we went around, for different views from the rim. One of the views was much closer to Wizard Island. Looking in the other direction. What we didn't expect when we went on to see it was that we'd be stuck in a traffic jam for about 2 hours, I think it was. We made good time to get to the Crater Lake National Park. I think it's a national park, Crater Lake National Park, which was open, and you have to pay an admission to go into it. But the authorities, they've got like one kiosk and what seemed like one man on duty with about 2 miles of cars, all paying, and answering all sorts of questions, with lots and lots of people behind. So we were stuck in a traffic jam for a long, long time, waiting to get into the area. But it was well worth it to see. And I think that's the last picture.
Brilliant.
Just use the I mean, that is just spectacular. I don't know you, but I want to go. That is just superb. And I know the sun always shines on America, but that is just superb. So, can you all join me in thanking Alan in the usual way?